Random variable is simply a quantity whose value depends on chance. Some examples of random variables are number of girls in a class, number rolled on 2 dice, heights of boys in a class, time taken on homework assignment. The thing to note here is that x and t are what we call discrete random variables. They're distinguished because they are countable. H and A are continuous random variables, and they're unique because they are measurable. In probability, we're going to deal with the discrete random variables, and later on in statistics, we'll deal with continuous random variables. What we're going to do with the random variables is we're going to work with probability distributions, and we're going to do this with the discrete random variables. Really, all it is it's a table, and what it does is it gives a list of each possible value of the random variable and the probability of that outcome. Okay. What we're going to do, the steps, if you want. Steps will find all possible outcomes of a particular random variable, and we'll call it x maybe. We'll calculate the probability of each outcome. We'll use sample space, some type of sample strategy, and we'll put outcomes x and the probability into the table. So here's an example. We're going to let x, notice we use the capital letter X to denote the event, and that is the number of tails seen when 2 coins are tossed. And from the notation, the probability that x is equal to x is the probability the number of tails is, and then whatever number that is. All right. So what we have to do now is we have to restructure the problem so that we can represent each outcome of tails with a number. All right. So what we'll do is we'll represent this with a tree diagram. Usually find this easiest to do. So on the first coin, the possible outcomes are heads and tails. On the second coin, the possible outcomes are heads and tails. And again, each outcome has equal likelihood of occurring. So each probability is 1/2. We call this a weighted tree diagram. All right. And now the possible outcomes are heads, heads, which we will also represent as 2 heads. And then we have this outcome, next branch, heads, tails, or the following branch, tails, heads, both of which are the probability of 1 heads. Okay, this is all in terms of 1 heads. The bottom branch gives us tails, tails, which is 0 heads. All right. What we'll do is we'll calculate the probability of each of those. And again, we can use the tree diagram that we've just drawn. So the probability of tails, tails is 1/2 times 1/2, which is 1/4. Tails and heads is also 1/4. Heads and tails also 1/4, and heads and heads is also 1/4. Although you'll notice for the event 1 heads, both of these outcomes are represented by 1 heads, and so we can combine their probabilities to make 1/2. So there you can see that the probability of x equals 0 is 1/4, and that's tails, tails from the tree diagram. X equals 1 is 1/2, that's from the 2 middle outcomes, and x equals 2 is equal to 1/4, and that's from the top branch, which is 2 heads. So what we'll do now is, as we said in our steps, is we're going to put the outcomes, x, so the outcomes are the 0, the 1, the 2, and each of their associated probabilities into a table. So as you can see from this table, the outcomes x in the top row, 0, 1, and 2, the probabilities for each of those outcomes, 1/4, 1/2, and 1/4 as we calculated above. And what we can also do with this is we could also calculate the expected value. But we'll leave that just a little bit later. What's most important right now is that you understand these 2 really important rules at the bottom. Star it. 2 very important rules. first one just says that any probability in the table has to be between 0 and 1, which you can see from the table above, all of them are. And the sum of the probabilities must add up to 1, using the sigma notation, if you remember from last year. So again, really all this is saying is each individual probability must be between 0 and 1, which again we've kind of talked about a bit already, and then the sum of the probabilities, again, within this experiment, the sum of the probabilities must all add up to 1. All right, so here we'll do a problem. So we're given these different probabilities. The probability of the outcome x equaling 0 is k. The probability of the outcome x equals 1 is 2k. Probability of the outcome x equals 2 is 3k. And the probability of the outcome x equals 3 is just k. The direction here should say to find k. All right. So what we'll do is we'll put this into a table. So we have all of our outcomes x here, and those different outcomes are x could be 0, 1, 2, or 3, and below the probability that the discrete random variable x is equal to that variable. So in the first column of the table, the outcome 0 has a probability of k, the outcome 1 has a probability of 2k, the outcome 2 has a probability of 3k, and the outcome 3 has a probability of k. And so now to find k, we're going to use one of the rules we just talked about on the previous page, and that is that the sum of the probabilities must add up to 1. And so this is really simply done. Just add up the probabilities, k plus 2k plus 3k plus another k equals 1. You add up the k's, should be 7k equals 1, and so we find that k is equal to 1/7. This is quite often a style of IB question that's given to you. Something to do with a table with a missing probability. Again, you have to know that the sum of the probabilities adds up to 1. In the next example, we're given the probability distribution is represented by a formula, k over x, but we'll just do the same thing. All the different outcomes that are possible are the numbers 1 to 6, and the probability of each outcome is based on its value. So what we'll do first is we'll make the table with the various outcomes and the probability of each of those outcomes. So there, again, our outcomes could be the numbers 1 to 6, so 1, 2, 3, 4, 5, and 6. And the different probabilities would be k over 1, k over 2, k over 3, k over 4, k over 5, and k over 6. And now to find the value of k, we use that important rule again, that the sum of the probabilities must add up to 1. So we can express this as k over 1 plus k over 2 plus k over 3 plus k over 4 plus k over 5 plus k over 6 adds up to 1. Obviously, to combine these, we need a common denominator, and you can see to work with 6 and 5, it needs to be at least 30. To work with 4, it would need to then be 60. So our common denominator will be 60, and we'll just multiply each numerator by the factor that's required to make 60. So it'll be this, it'll be 60k plus 30k plus 20k plus 15k plus 12k plus 10k equals 1. And we add those all up, and we get 147k over 60 equals 1. And then solving for k, we get k is equal to 60 over 147. And now we can answer part B, now that we know k. So to find, in B, we want the probabilities. The probability that x is greater than or equal to 3 and less than or equal to 5. So really what we want from the table is we want probabilities k over 3 plus k over 4 plus k over 5. So now that we know k, we have 60 over 147 over 3 plus 60 over 147 over 4 plus 60 over 147 over 5. And if you remember some of the things that we talked about with fractions, each of those fractions in the 3, the 4, and the 5 will move into the denominator, and we can divide them with the 60, and the common denominator will still be the 147. And so 60 divided by 3 is 20, 60 divided by 4 is 15, 60 divided by 5 is 12, for a total of 47 over 147. And that would be the probability of finding any value between 3 to 5, including 3 and 5. Next, we're going to talk about expected value, or mean, as it's sometimes referred to. You might see it use the symbol mu. It looks like a U with a tail in the front. The expected value, or the mean of a random variable x, is the average value we would expect for x over many trials of the experiment. The notation is E, it looks like E of x, okay? It's the expected value of x. Simply, it's the summation of each outcome multiplied by its probability, as can be seen in the formula in the orange box. Again, summation of each outcome multiplied by its probability. Once you have the information arranged in a table, it's very easy to calculate. In question 4, or in example 4, in a game of chance, the player spins a square spinner, and the numbers are 1, 2, 3, and 4, wins the amount of money shown in the table, depending on which number comes up. So again, what we're going to have to do first to answer the expected return for one spin of the spinner is we first have to find all the probabilities and the outcomes. So we'll make the probability distribution table. So the outcomes are actually the winnings. Okay, so it's 1, 2, 5, and 8. And since it's a square spinner, we're assuming it's a fair square spinner, each face has equal likelihood of showing, so it's each face would have a probability of 1/4. The expected value now for this would be calculated by taking each outcome, so the 1 times its probability 1/4, plus 2 times its probability 1/4, plus 5 times its probability 1/4, plus 8 times its probability 1/4. And add these all up. The numerators are going to be 1, 2, 5, and 8. If we add those, we get 16 over 4, which would be 4. And that would be represented by $4 because the outcomes in the question are in dollars. It's really important to note here too that the expected value does not have to be one of the outcomes that are given in the table. So you'll notice that our expected outcome is $4, but $4 is not one of the individual outcomes in the table. And that's okay. We can have that answer. What we'll do now is we'll answer part B. It says if the game it costs $5 to play, so I'm going to answer part B over here. If the game costs $5 to play, would you recommend someone to play it? Well, the expected outcome, including the money that you have to pay to play, space here. Again, you're expecting to win $4 every time, but if you're playing, it's a sure thing, so it's going to be $5 times 1, and so on every play of the game, you can expect to lose $1. So this would not be recommended to play because going into the game you can expect to lose $1. And again, it may not happen every time, but again, this, like the definition says, we can think of this as a long-term weighted average. All right, so after you play the game many times, you would end up being down $1. In example 5, a person plays a game with a pair of coins. If a double head is spun, $10 is won. If a head and tail appear, $3 is won. If a double tail appears, $5 is lost. All right, so how much would a person expect to win playing this game once? All right. So again, we're going to set up our probability distribution table, and in it we'll put the outcomes, the different outcomes. Again, the first outcome would be losing 5. That would be for an outcome of zero heads or a double tail. Again, from the probabilities that we found earlier in this lesson, we know that that probability is 1/4. All right. If a head and a tail appear, the person wins $3. Again, this is done from the perspective of the player, right? For probably 1/2. And if a double head is spun, which again would be 2 heads, the outcome is a win of $10, and that has a probability of 1/4. So now to answer part A, how much would a person expect to win? So the expected value would be, again, the summation of each outcome times its probability. The calculation would look like this. It's -5 times 1/4 plus 3 times 1/2 plus 10 times 1/4 for a total of 11/4. And since we're working with money, it makes sense to convert this to decimal. So 2.75, $2.75. And it says if the organizer of the game is allowed to make an average of $1 per game, how much should be charged to play the game? Well, again, since this question is designed from the perspective of the player, all right, if the organizer is allowed to gain or make $1 from each play of the game for the player, then he would expect his expected value should be -1. Like this, -1. So again, in the end, he should be down 1. But when he plays the game, he can expect to win 275. But he has to put something in to play the game. So the amount that he puts in will be X, and that's a sure thing. To play the game, you have to pay. And to calculate X now, X would equal -375. And again, this is from the player's perspective. So this would be the player, this would mean that the player would pay $3.75 to play the game. All right. And the last question, I'll do in class as an example. It takes a little bit of time to solve. So now go ahead and try the homework questions or the homework check questions for this lesson.